5.4, number 3, you said? 5.4, number 3. Here we go. The figure at the right shows a box M2 of mass that, on a frictionless plane inclined at 30 degrees, it's connected by a cord of negligible mass. The pulley is frictionless. If the magnitude of the horizontal force, what's the tension in the cord? Okay, great. So here we go. So, do we know this one? This guy is 3 kilograms. This guy is 1 kilogram. We're going to push M1 with a force of, in part A, 2.3 newtons, right? We know that this angle here is 30 degrees. And based on that, we're trying to find the tension in the cord. All right. Yeah, this is great. This is a great problem. Okay, so thoughts about how to start, you guys? What should always be our first step anytime you have an inclined plane, you guys? Split up your forces into components, right? So I'm going to... All right, so force of gravity on this guy is going to be 9.8. So if you find your components, your FG parallel is going to be negative... Oh, which way do you want to make positive, you guys? You want to make this way positive? Okay. So 4.9 newtons is your FG parallel. I'm not even going to worry about the perpendicular and normal forces. Is that cool? Yeah. Why don't I need to worry about that? There's no friction, right? Okay. Now, we've also got this force over here that's 2.3 newtons, and the problem wants to know the tension in the cord, right? Okay. So I guess, do you know what I would do, honestly, I guess I would start by making sure that the rope doesn't go slack. You guys see what I'm saying? Isn't it possible that the rope might go slack? All right, now I can quickly see that it doesn't by putting in these masses. Look, if this is 3 kilograms and this is 1 kilogram, which box is going to accelerate faster? The 1 kilogram one, right? Because it's got less mass and more force on it, right? Yep. You guys, does that make sense? Yes. All right, so I can quickly see the rope's not going to go slack because if they weren't attached, the bottom block would go faster, right? Follow? All right, so the fact that there's a rope attaching them means they're going to move together. Good. All right, are there any other forces I need to consider that are going to affect the motion of the system? I think that's it. It's frictionless, right? Okay, cool. So let's find, what should I do now, you guys?
Acceleration of the system.
Find the net force and acceleration of the system, right? So let's see. So the net force is going to be, well, it's just the sum of these two, right? 4.9 plus 2.3, which gives you a 7.2 newtons, right? Follow? And so my acceleration of the system is net force over mass. I got 7.2 newtons pushing this thing in a positive direction. The mass is 4 kilograms. So divide this and you get 1.8 meters a second squared, right? Dan, you good up to there? Everybody good up to there? All right, now what? Sure.
Well, you can look at the 3 kilogram box and you know that it has tension pulling it downwards, so then you can do net force equals net force.
Good, yeah. At this point, pick one of the two boxes and solve for your tension, right?
Well, it'll probably be easier to do the bottom one just because its mass is 1.
Yeah. Does it matter which box you pick? No. A good way to check would be to do both, right? Okay, so I'm going to do the 3 kilogram box for no real reason. All right, so here's the 3 kilogram box. Here's what I know. I know there's an applied force of 2.3 newtons on it. And I know tension is pulling it forward. I know the acceleration is 1.8 meters a second squared. So what should I do? Find the net force, right? So 1.8 times 3 is what, 5.4 newtons, is that right? So now I can solve for the tension, right? And it's going to have to be what, 3.1? Cam, you good? Yeah?
Well, I set mine up differently, and I don't get why it didn't work.
Tell me what you did.
So I set
acceleration of the two boxes are equal, so I did 2.3 plus the force of tension over 3 kilograms, so it's like net force over
Right on, I gotcha. Yeah, but this is great.
equals the 4.9 minus the force of tension over 1 kilogram, and then I solved for force of tension, and I got,
That should work.
I don't know if I
So what you're doing is you set up an equation for the acceleration of this, you set up another equation for the acceleration of that, and then you set them equal, right?
yeah,
That should work. Let's try it.
I must have just screwed up in there.
Yeah, I think you might have just made a little math mistake, like an algebra mistake or something, right? But let's see. So the acceleration of the 3 kilogram box is going to have the 2.3 newtons and the tension, right? And the 1 kilogram box is going to have the 4.9. Did you make the 4.9 positive or negative?
Positive.
Okay. And you made your tension negative, right?
Yeah.
That all jives, and it's 1 kilogram, right?
Yeah.
So I think this works. So let's see. We've got 2.3 plus the force of tension over 3 kilograms, right? So that's the acceleration of this guy.
Yep.
That should equal 4.9 minus tension over 1 kilogram, right?
Yeah.
So what'd you do? Cross multiply maybe?
Yeah, so I got 2.3 plus the force of tension equals 14.7 minus 3 force of tension.
Yeah, that should work. So 2.3 plus the force of tension equals 14.7 minus 3 FT. So add 3 FT and subtract the 2.3.
Yeah, I see what I did.
You got it?
Yeah.
So this works.
Yes.
Great. So what does that give you? 12.4 and then divide. You should be good. Good, you guys?
Yep.
All right. Do you guys understand what I was saying about ensuring that the rope doesn't go slack?
Yes.
Good. There? All right. Oh, that's question B. Oh, yay. All right. So before I do, Carla, are you good on this? So this is the acceleration of the top box. This is the acceleration of the top box. Or the bottom box.
Why didn't you just do like net force equals mass times acceleration
For what?
for the one box, and then you could just say like
Yeah. Because it's so.
I was just doing it the way that
Yeah, I
Cam
can
did
do
it.
it that way. That's how I do it all the time.
Yeah, so the way I did it was, I think what you're saying, was I found the acceleration, and then, yeah, I just did net force equals mass times acceleration. And solve for the missing force.
okay, I'm just not getting the right answer.
When you do what?
That
This?
yeah. Maybe I just did it in my head wrong.
All right,
Yeah, I did it in my head.
so you're good?
Yeah.
All right, cool. So let's do part B. It says, what's the largest value the magnitude of F may have without the cord becoming slack? So let's go back to the original problem. Let me kind of make a new drawing here to kind of clean things up a little bit. All right, so here we go. So once again, we've got a 3 kilogram thing and a 1 kilogram thing. FG parallel on this guy is 4.9 newtons, right? All right, so there are a couple of ways of doing this, all right? There's sort of an intuitive way to do it and a mathy way to do it, all right? Let me do it both ways, all right? So the intuitive way to do it is we're going to apply a force on this thing, right?
Yes.
So describe to me something about the motion of the two boxes when the rope goes slack. So what do you got, Zach?
So the acceleration of the 3 kilogram box is greater than the 1.
Good. Does that make sense? The rope will go slack if this has an acceleration that's bigger than this is acceleration. This is, as in belonging to this.
But does it have to be bigger than the parallel acceleration?
Yeah. Oh,
Like which acceleration does that have to be?
yes, the parallel.
Like the okay.
So in other words, if this rope wasn't here, so with no rope, the acceleration of the 1 kilogram thing would be net force over mass, which is 4.9 newtons over 1 kilogram, which is 4.9 meters a second squared, right?
Yes.
Follow? So, how do I make this 3 kilogram thing accelerate at that rate? So, 3 kilograms accelerating at 4.9 meters a second squared. Well, let's see. Net force equals mass times acceleration. I've got 3 kilograms, and I want to accelerate it at 4.9 meters a second squared. So multiply it and get 14.7 newtons. So if this force is 14.7 newtons or more, then my tension will be 0. Follow?
So basically, you take out the rho first to find the acceleration,
Yes.
and then you put it in.
Make sense or no?
Yep.
Okay. Let's see. There's a mathy way to do this too. How does that work again? Oh, yeah. Cam, go ahead.
So with the roughest slack, can you just assume that tension is 0?
Exactly.
Then you can just like solve.
And then you can do exactly what you did before, right?
Yeah.
So the other way to do it is to go, all right, well, I know that the 3 kilogram box is going to have a force applied to it minus 0 tension over 3 kilograms, right? And that's got to equal the 1 kilogram box has got the FG parallel, which is 4.9 minus 0 tension over 1 kilogram. Okay, and yeah, it boils down to the same thing, same difference. Cool, you guys? All right, so that's good. Make sure you understand that. That is an important concept that came up a couple other times on these problems.
It will be on the test.